Okay, we're going to start section 4.5 here, which is curve sketching. Now at this point, we're going to kind of put together everything that we've learned in algebra and trig, and now the things that we've done in calculus, and we're going to be sketching graphs. Okay, and of course the things that we've talked about earlier about the derivatives, okay, first derivative test, second derivative test, concavity test, and even things with limits are very useful to us when we sketch a graph. So that we're all on the same page here, here's a list of 10 steps that I would like us to be using when we sketch a curve, okay? This is pretty much how the book is going to be doing it too, okay? So step 1, we're going to state the domain of the function. Step 2, we're going to compute the intercepts. Step 3, we're going to check for any symmetry, or if it's periodic, of course you'd only do that if you're working with trig functions. Now step 4 is where the calculus would begin. Okay, compute all the possible infinite limits and limits at infinity for the function, and then we'll be able to state the asymptotes based on our work in problem 4. Now, of course, we already know from algebra how to determine asymptotes on occasion, okay? So it's going to be sometimes the case that we would be able to know those equations earlier in the problem without any limit calculations there, okay? But sometimes not. Step 6, we're going to compute the first derivative and find the critical numbers. Step 7, we're going to use the first derivative test to find the local extrema. Now, we did talk about the second derivative test. I would like us to use the first derivative test in step 7 just because in the case of the second derivative test, it can sometimes fail, you know. I've noticed that in the book they're mainly using the first derivative test. That's the more common approach, okay. We will use the second derivative test for some other things though in another section, okay. All right, step 8, we're going to compute the second derivative and then find the x values for which f double prime of x is 0 or f double prime of x does not exist. And then with those key numbers, we'll apply the concavity test and we'll find the inflection points. That's step 9. Now, at this point, we should have a lot of information. Okay, in step 10, we're going to graph the function with an appropriate scale, and then, of course, we can use our graphing calculator to check the answer. Now, of course, be sure that the work is shown for these steps. Okay, that's really where the bulk of the points are going to be in grading a problem like that. You know that the work is there. Okay, so I've got some examples. This section is going to likely take several videos to get through. So, let's go ahead and take a look at. Here's one example. I want to graph the function f of x. Which is 2 times x squared minus 9 over x squared minus 4. Okay, and I'll just kind of go through the list of steps here, and then I'll sketch a graph at the end. Step 1, we need the domain of the function. 2 and negative 2 would be a problem. I know I can't divide by 0, so I'll throw those numbers away. And of course, because I'm throwing those numbers away, I know I'm going to have corresponding vertical asymptotes at x equal 2 and x equal negative 2, right? That's step 5. We'll get there later. Step 2, I need to find the intercepts. So to find the x-intercepts, I need to let the function be 0 and solve for x. I've done that. Multiply both sides by x squared minus 4 and then divide by 2. X squared minus 9 equals 0 means that x squared is 9. If you take the square root of both sides, x would be 3 or negative 3. And then to get the y-intercepts, you're going to let x be 0. When you plug 0 into the function, you get, it's going to be negative 18, or excuse me, yeah, negative 18 over negative 4 is 9/2 when you reduce. Okay, so these 3 points would be the 3 intercepts on my graph. Step 3, I want to check if there's any symmetry for the graph. Okay, now in algebra, you learn about even and odd functions. If f of negative x and f of x are the same for all x, then f is an even function, and an even function is always symmetric to the y-axis. If f of negative x and negative f of x are the same for all x, then f is an odd function, and an odd function is always symmetric to the origin. Okay, so here's our function, f of x. If I replace x with a negative x, negative x squared is the same as x squared. So I would get exactly the same function that was originally there. And so therefore f would be even, and it is symmetric to the y-axis. Okay, so that can be helpful when I sketch this. There's going to be some symmetry going on. Step 4 is where I want to find all the infinite limits and limits at infinity. Now remember, an infinite limit is a limit that's going to return infinity or negative infinity or does not exist. A limit at infinity is where x is approaching infinity or negative infinity. Okay, so I want to find all those limits here in step 4. Well, I've already mentioned earlier that 2 and negative 2 are not in the domain. Okay, so I'd want to be calculating infinite limits around those numbers, those two numbers there. If we were to take a look at the limit as x approaches negative 2 from the left of f of x, well, if I'm on the left side of negative 2, like let's say x is negative 2.1, okay, then the numerator is going to be a negative. The denominator will be a small positive. And of course, the closer that you are to negative 2, the smaller the positive number is. A negative divided by a small positive would produce a large negative. Okay, so the value of that limit would be negative infinity. How about if I'm on the right side of negative 2, like x is negative 1.9? Well, you're going to get a negative in the numerator, and you will also get a negative in the denominator, since when you square a number that is a little bit bigger than negative 2 but close to negative 2, and then you subtract 4, you're going to get a negative number, a very small negative number, okay, as is the case with like negative 1.9, for example. Negative 1.9 squared would be some number less than 4, so when you subtract 4, you'll get a negative there. A negative divided by a small negative would produce a large positive output. So the result of that would be infinity. Okay, how about the limit as x approaches 2 from the left of f of x? Well, if I'm on the left side of 2, like let's say x is 1.9, I will have a negative in the numerator and a negative in the denominator. Okay. Just like I did when x was negative 1.9, right? Because I'm squaring x. So the negative divided by a small negative would produce a large positive. And if I'm on the right side of 2, like let's say x is 2.1, okay, you're going to have a negative in the numerator and a small positive in the denominator. Of course, the closer that you are to 2 on the right, the smaller this positive would be. Okay, a negative divided by a small positive would give you a large negative output then. The limit as x approaches infinity of f of x, you could use L'Hopital's rule on that if you want. That's what I'm doing here since I'm in indeterminate form, infinity over infinity. 2 is a constant that can come out of the limit there, and the derivative of the top would be 2x, derivative of the bottom is also 2x. Those cancel, right? Limit of a constant is always the constant, so 2 times 1 is 2. Okay, the limit as x approaches negative infinity of f of x would also be 2 by using symmetry. Okay, we've already said that the graph is symmetric to the y-axis. Or I could use L'Hopital's rule. Okay, the calculation would be the same as it was, only you're approaching negative infinity. Now, the fact that we had these any one of these 2 calculations done means that we have a vertical asymptote at x equal negative 2. Either one of these 2 calculations would indicate that we've got a vertical asymptote at x equal 2. Now, we already knew that from earlier, right? We're throwing away 2 and negative 2 as a result of the domain. We already know that we're going to create vertical asymptotes from what we already know in algebra. Now, we're also going to have a horizontal asymptote at y equal 2. Either one of these 2 limit calculations tell us that. But, again, going back to algebra, we can already know that in the case of a rational function, whenever the degree of the top is the same as the degree of the bottom, you're going to have a horizontal asymptote, and you can get that very quickly by just comparing the coefficients in front of the leading terms there with the highest degree. So I've got a 2 in front of x squared up top, a 1 in front of x squared down under. 2 over 1 is 2. Y equal 2 is a horizontal asymptote. Okay. Now be sure that when you write the asymptotes, they are written as equations. I've mentioned this before, but still worth repeating. Okay, like don't just write 2. Okay, because that can be misleading. You know, somebody could think that, oh, we're talking about y equal 2, okay, or x equal 2. Okay, or you know, if we just write negative 2 here, somebody could think, oh, that's y equal negative 2. Well, no, we don't have y equal negative 2 as a boundary, right? So be sure that it is written as an equation. Okay. Step 6 is where we want to compute the first derivative and then find the critical numbers. F prime of x is going to be a quotient rule. So we got the bottom times the derivative of the top. The derivative of 2x squared would be 4x, and then minus the top is 2 times the quantity x squared minus 9 times the derivative of the bottom. That'd be 2x, and this is all over the denominator squared. Okay, simplify the numerator, and let's see, you're going to have 4x cubed from this part, minus 4x cubed, those are gone, and negative 16x, negative 16x plus 36x would be 20x then in the numerator. Okay, set that equal to 0. If you multiply both sides by the denominator, that clears out the fraction for us. 20x equals 0 means that x is 0. 0 is a critical number. Now, 2 and negative 2 are a problem in the denominator, but those are not critical numbers. They're numbers that I'm going to use in the table, but they're not technically critical numbers. Remember, a critical number is a number that has to be in the domain of f. 2 and negative 2 are not in the domain of f. I will still use those numbers in this table that I create when I use the first derivative test. Remember that in the table, you're always going to include the numbers that are the critical numbers along with any numbers that are going to produce vertical asymptotes on the graph. Okay, so I want to make sure that all 3 of these numbers are on my table, only, of course, 0 is the only critical number though. Okay, so I've got my interval, number chosen, value of f prime, and then the conclusion. These 4 intervals have been created here, separating, splitting up the number line. And now I can choose my test values. So like if x is negative 3, and I plug that in here, I'm going to have negative 60 divided by 9 minus 4 is 5, squared is 25. That's a negative, so it'll be decreasing on that part of the graph. If I let x be negative 1, the second interval, plug that in here, I'm going to have negative 20 divided by negative 3 squared is 9. Okay, so that's a negative value of f prime. We're still decreasing. If I were to let x be 1 in the third group, 20 divided by negative 3 squared is 9. It means you get 20 over 9. That's a positive, so we're increasing on that part of the graph. And then in the last group, if we let x be 3, 20 times 3 is 60, divided by 5 squared is 25. That's a positive. We're back increasing again. Okay, we are changing from decreasing to increasing. That's going to produce a local min on the graph. It's going to produce a local min when x is 0, and when x is 0, we've already said that y would be 9 halves, right, when you plug 0 into the function. Okay, so that y-intercept is also a local min when I go to draw this curve here. Now we're on step 8. Okay, step 8, we need to find f double prime of x. So that's going to be a quotient rule. Of course, make sure that when you're finding f prime, you simplify, okay, because you'll need to find f double prime here. Now inside the quotient rule, I'm going to also need a chain rule here when I differentiate the denominators. So let's go ahead and begin that. We've got the bottom times the derivative of the top is 20, minus the top is 20x times the derivative of the bottom. That'd be a chain rule. It's going to be 2 times x squared minus 4 times the derivative of x squared minus 4 is 2x. And this is all over the denominator squared. X squared minus 4 squared. Squared would be x squared minus 4 to the 4th. I'll need to set this equal to 0, so of course I'll want to simplify. Now, to begin simplifying, x squared minus 4 is in common to these two groups in the numerator. Let me go ahead and factor out an x squared minus 4 from these two groups, and I'm going to cancel that with one of the 4 of them in the denominator. That way I'll only have 3 of them left in the denominator. Okay, so that's what I'm doing here to start. One of these x squared minus 4 terms has been factored out and canceled, so you're going to have one more remaining, times 20, and then minus, this x squared minus 4 has been factored out and canceled, so you're going to be left with the other things here, minus 20x times 2 times 2x. 20x squared minus 80x squared would be negative 60x squared, and then I've also got minus 80. And when you set that equal to 0 and solve, multiply both sides by the denominator to clear out the fraction, and if you add 80 and divide by negative 60, you'd have x squared equal 80 over negative 60. There's going to be no real solutions to that equation. Okay, there'd be imaginary solutions which we don't care about, when we sketch this graph here. So now when I go to use the concavity test, remember I'm still going to include the numbers for which f prime of x does not exist. Okay, like in this problem here, there's still an issue with x being negative 2 and positive 2, right? Of course, I already know that there's vertical asymptotes at x equal 2 and x equal negative 2, but I'd still like to know what's happening around those asymptotes as far as are we concave up or concave down. So I'm still going to create a table here and include those two numbers, 2 and negative 2, and that'll split the number line up into 3 sections, and I've got my 3 intervals written here. I'll say interval, number chosen, value of f double prime, and then the conclusion. Now let's select our test values. If x is negative 3, and we plug that into f double prime, negative 3 squared is 9, and times negative 60 minus 80, that'd be a negative, divided by negative 3 squared is 9, minus 4 is 5, 5 cubed is 125. Okay, in the numerator we have a negative. Actually, if you were to simplify that, you'd get negative 620. Divided by 125, that'd be a negative. So we're going to be concave down on that part of the graph. Number in the middle interval would be 0. Okay, if we select that as a test value and plug that in here, we're going to have negative 80 divided by negative 4 cubed is negative 64. Negative over negative is positive. And so we're concave up on that part of the graph. And then if I select 3 as a test value here in this third interval, I should get the same output as when it was negative 3, right? Because I'm squaring x. Negative 3 squared is the same as 3 squared. So I'm going to get the same negative 620 over 125, which means that I'm concave down again. Now I switch concavity twice, but there are no inflection points, right? Because 2 and negative 2 are not in the domain of the function. Okay, so I should have plenty of information here to begin drawing this. At this point, I just kind of run through the information that we've already got in our from these earlier steps, and I put it on the picture now. So I'm graphing f of x. I've got 3 intercepts. Here's negative 3, 0, here's 3, 0, here's 0, 4.5. Okay, the graph is symmetric to the y-axis, and so I'll use that when I draw this. The limit as x approaches negative 2 from the left is negative infinity. That means that the curve is heading downward on the left side of that vertical asymptote. The limit as x approaches negative 2 from the right of f of x is positive infinity, so we'll be heading upward on the right side of that vertical asymptote. Limit as x approaches 2 from the left of f of x is infinity. We're heading upward on that side of the vertical asymptote. We're heading down on the other side there. You can see we've already got the asymptotes stated, right? Y equal 2, x equal negative 2, x equal positive 2. We've got one critical number. There's a local min at this point here. We change from decreasing to increasing. That's going to produce a local min. We are decreasing to the left of negative 2. So a tangent line to the curve is always going to be a negative slope. You can see that. We are increasing to the right of 2, so a tangent line is always going to produce a positive slope. You can see that. Okay. What else? So then we are concave up. Between negative 2 and 2, tangent lines all have to lie below the curve. Concave down on the other 2 sections, tangent lines all have to lie above the curve. So, this is all kind of coming together here when I draw this. And what you see here would be a quick sketch then of the graph of f of x. Okay. And of course I can check that using my graphing calculator. Like I would encourage you to do that. Once you've drawn this by hand, be sure that you have something that is correct. But again, make sure that the work is all there. This is what I'm grading you on, for problems in this section.